Welcome to 11.3. We are looking at the areas of regular polygons. We want to find the area inside of this polygon. So I've made this polygon a little bit bolder black here. You might want to do that on your notes also so that you understand we're talking about the polygon on the inside, not the circle on the outside. The circle is just as a point of reference because there are similarities between our regular polygon and a circle that we will talk about in just a minute. But before we jump into that, our essential question is, how do I find areas of regular polygons? And what does the word regular mean? Let's remind ourselves that it is equilateral, means each of these sides are the same length, they are congruent with each other. And equiangular, each of these interior angles are also congruent, they have the same measure. So when you see the word regular, you know that's a technical term that means equilateral and also equiangular. So here's our regular polygon, and let's identify some features of this that will make it easier for us to talk about and to pick apart and to be able to find the area for. That's our goal, to find the area. So here's the center of the regular polygon, which is also the center of a circle that circumscribes this regular polygon. Circumscribes, you circumscribe the globe, you go around the earth, circumscribe. This circle circumscribes the regular polygon, meaning that it goes through each of these vertices of your regular polygon. And radius goes from the center out to a vertex. Let's go ahead and label that dude there as, let me do it in a pen. Do I have a pen? I don't, so I guess I'll do it in pencil. Vertex. So your radius goes from the center out to a vertex. And notice that we have a number of vertices around here, and so therefore we can have a number of radii. So each one of these segments going out from the center to a vertex is a radius. In contrast to, or make sure you differentiate from, the apothem. That's how you pronounce that strange word. Not opossum, that's an animal. This is apothem, and it goes from the center to the midpoint of a side. So put a big old fat point there and a capital M referring to midpoint. That is your apothem. And notice that it is the perpendicular distance. So this is a right angle from the midpoint of a side to the center. Another feature that we want to talk about is the central angle. The central angle is the measure of the angle between consecutive radii. So here is a radius going from the center to the vertex, and the next radius going around either clockwise, this is going counterclockwise, or clockwise, is going to be your central angle. So you see that we have a number of different central angles here. In fact, there's one here, here's another one, 2, 3, 4, 5. I think I messed it up, didn't I? I did. So let's label those. Here's another radius, and here's another radius. It's going from the center out to a vertex, and here's another radius. There we go. So don't confuse it with your apothem. So here is, and there's, also didn't get this one, did I? So here's another radius. And of course this guy over here is also a radius. So the angle between consecutive radii is the central angle. So there's 1, 2, 3, 4, 5, 6. 6 different central angles going around this regular polygon. And notice that's the same number of sides that we have. There are 6 sides to this regular polygon, therefore it's a hexagon. And with 6 sides, that creates these 6 central angles. And we can calculate that central angle because we know that it's 360 degrees all the way around in one circle. Therefore, to calculate the, I really should have a pen. To calculate the central angle, all that you have to do is take 360 here, and then divide it by the number of sides. 360 divided by the number of sides, and that will give you your central angle for a regular polygon. So in this particular case, it's 360 divided by 6. There's 6 sides, and that gives you 60 degrees. Okay, so this angle, the central angle here is 60 degrees. Now notice that when we have this apothem, it is at a right angle, and so this also is at a right angle, and so these two triangles are congruent with each other. So therefore this apothem is an angle bisector of this central angle. We said the central angle in this particular case is 60 degrees, so this small angle here is going to be 30 degrees. That's going to be helpful. We're going to need to know that in the future here. Okay, so let's do an example from your textbook, and I'll show you how we can separate this. So here is a regular polygon, we are told, and in fact it's a pentagon. There are 5 sides to this dude, and going from the center out to a vertex that is a radius here. So here are 2 radii, and I've gone ahead and drawn the other radii. And you can see that there are, just as there are 5 sides, so also there are 1, 2, 3, 4, 5 central angles. And so if I wanted to find the measure of this central angle, all that I do is take my 360 degrees, the angle all the way around, and then divide it by the number of sides, which is 5. 360 divided by 5 is 72 degrees. So this central angle, in fact each of these central angles, is 72 degrees. And now they're asking for what is the measure of the angle between the apothem and this radii. And like I said, these 2 triangles are congruent with each other. Therefore, CP, CTC, corresponding parts of congruent triangles, are congruent. So these 2 angles here are congruent. This apothem is an angle bisector to this central angle. So the entire central angle was 72 degrees, and divide that by 2, and that gives us 36 degrees. So if I was to take this right triangle here and blow it up, make it bigger, then you would see that here is your right angle, and this angle up on top, this small angle, is half of the central angle. That's 36 degrees. And the other angle that we need to find is down here. So it's this bottom corner angle, and that one is, in this case, 54. How did I get that? Well, you know that the sum of the interior angles of a triangle is 180 degrees, and adding 90 plus 36 gives us 126. So 180 minus 126 gives us 54 degrees. So this angle here is 54 degrees. Okay, so you are ready now to do your problem here. And we are looking, with this problem number 1 on your notes, we're looking at this regular polygon. This is a quadrilateral, and remember when we say regular, so it's a equilateral and equiangular, and a regular quadrilateral is a square, as you know. And so identify the center. So which of these points is the center? That's not too hard. You can figure that out on your own. And also label the radii. So give me the designation for a radius. Here is one, here is another, and go ahead and draw in these other radii, and also list them here for each of the radii, for each of the 4 vertices. And then apothem, there's one that is labeled here. These others, you can draw them in, but we do not have points designated for them, so just give me the designation for the one apothem that is labeled. And then also give me the designation for the central, or one of the central angles. In fact, how many central angles are there in this guy? There's going to be 4, because there's 4 sides. So in fact, why don't you go ahead and write out all 4 central angles. So in other words, angle what and what. There's actually 3 points that you want to use for the designation of any angle. So what are the 3 letters that follow here for the first central angle, and then do each of the other 3 angles after that. And then with regard to this same diagram, find the measure of angle XPY. XPY, okay, that is a central angle. I've made that in red just to make it a little bit clear. This larger angle here. And so how would you calculate that central angle? As you know, it's 360 degrees all the way around. And how many central angles does this regular polygon have? And it's the same as the number of sides. There's 4. So 360 divided by 4. And so put that calculation there and also the answer. And then the measure of angle XPQ. So they're asking for this angle. So what is the measure of this green angle? Remember, that is half of your central angle. So once you find the central angle, then take half of that. And then this purple angle. So notice here, first we're talking about this isosceles. This is an isosceles triangle here because these radii, of course, are the same length. So here's an isosceles triangle. But now let's just focus on this right triangle here. And what I'm doing is taking this right triangle and bringing it over here. So I'm kind of flipping it over. And so drawing it so it's a little bit easier for me to be able to see. It really is the same triangle as we have over here. So we could take this one and bring it over here. All the measurements will be the same. So this angle up on top is half of your central angle. That's the measure of that angle. And then you know this is 90 degrees. So to find this side angle, remember the sum of the interior angles is 180. So add 90 plus whatever half of your central angle is, and then subtract that from 180, and you'll get the measure of this angle on the side there. Okay, so go ahead and pause the video and do that on your own. Now let's talk about finding the area. How do you find the area? This is nice to pick this thing apart and understand how it all works. But let's use that to find the area of this regular polygon. And notice that when I do break this thing down, here's the apothegm and radii and so forth. Notice that I have a whole bunch of triangles, and each of these triangles are congruent to each other. So what is the area? What's the formula for the area of a triangle? It's 1/2 base times height. So let's just look at this one small triangle here. And my base, let's call it this green segment here, and the height is going to be your blue. Notice though that your height of the triangle is your apothegm. And the base, in this case, is half of the side. And if I was to take all these little triangles and then cut them apart and spread them out, it would look something like this here, because there are 1, 2, 3, 4, 5, 6. There are 6 sides on this, so I have 6 of these isosceles triangles lined up here. And notice that this red, this length here, is actually the perimeter around your regular polygon. And so to find the area of this regular polygon, or the area of these 6 triangles, what I can do is use